Hello and welcome to Queer Math. My name is Jess. As you can see, I am a trans girl and I'm also entering my second year in a math PhD program. My first year just got done and it was kind of rough, but I got through it and I'm excited for the years to come. So today I thought that I would just talk about the question like what is math, or more specifically what I usually get asked whenever I tell someone that I'm a math PhD student or that I'm researching math. They're like, what is math research? What does that look like? Because I think a lot of people have kind of their understanding of math from like high school classes that they took, or maybe like a calculus course in college, but people don't really understand like what comes after that. And so I thought that I would talk a little bit about that today. The first thing that I really want to say is that math is a lot like learning another language. With a lot of areas of expertise, you have a whole bunch of jargon that you need to learn. And with math, the thing is that the objects that we're actually studying, the things that we're actually doing our research about, are abstract ideas that themselves are kind of buried under jargon, which is why a lot of times it's hard to describe what math research is to people who aren't already familiar with what math is like. So if I had to give like a one sentence summary of what math is in kind of the most general yet concise ways, I would probably say that math is the study of abstract ideas that has very formal and rigorous foundations. So we know that the things that we're saying about these objects are really true because we have like a level of proof for the things that we're saying. That's what I mean by like the formal and rigorous foundations. The thing about abstract objects is that all of the things that mathematicians study are just things that kind of exist like in the mind or like just on paper. It don't really exist in the real world anywhere, right? We may have an idea of what one thing is, right? I have one poster, but that's not the number one itself. The actual number one is an abstract idea which we place onto the world. So I thought what I would do is to give people maybe a better idea of the sorts of abstract ideas that mathematicians are actually studying or talking about. I would give a relatively simple example of a more abstract idea, which is what's called a metric space. So mathematicians really like to generalize. We like to see things, see ideas that we have in the real world or even in other areas of math, and we like to boil those ideas down to their essential properties and then see what we can still find out about those objects when they're only just at their most basic elements. So metric spaces are themselves supposed to be a generalization of our notion of distance. In the real world, we can measure a distance between two objects just by setting up a ruler in between them, right, and figuring out what their distance is apart. But mathematicians came up with this idea of metric space because we don't always just have one ruler distance. We might have different ways of measuring distance between things. If you're a little bit familiar with, say, relativity, you may know that space-time is actually curved, especially around massive objects. So when we're trying to measure distances around these massive objects, we can't just use our ruler approach anymore. Instead, the actual distances that we measure are going to be different from if we just held up a ruler there. Or even on Earth. If you're trying to, say, get from London to LA, you're not just going to take the shortest path that the universe sees to get there, right? That would travel through kind of the center of the Earth. Instead, our notion of distance there actually has the curvature of the Earth in mind, right? Our distance isn't just what the universe sees as that straight line from London to LA, but it's actually whatever the plane flies over the surface of the Earth. So you can see that like even in the real world, we have different notions of distance. And so metric spaces are really supposed to be a generalization of that so that we can just study the core properties of like what it means to have a distance between things and then see what we can still get out. So more explicitly, a metric space is really just a collection of objects, of things that also has a function which tells us the distance between any two of those things, right? So we can just measure a distance between two things. So I'm calling it a distance function, but A lot of times it's also what's just known as a metric. But basically our distance function, we want it to have a couple properties. We want it to take in 2 points, and it should tell us a real number that says how far apart they are. So we put in 2 points and it says they're this far apart. We also want that number to satisfy a few different things. First of all, we want it to be 0 or greater. Right? Negative distance doesn't really make sense to us, so we don't want the number ever to be negative. And we also want that number to be 0 only if we're trying to find the distance from one point to itself. The second thing that we want to be true about this function is that if we're trying to find the distance from point A to point B, then that's going to be the same as trying to find the distance from point B to point A. Right? The direction that you travel shouldn't affect how far apart things are. And the last one is a little bit different from the first two, but basically what it says is that if we're trying to find the distance from point A to point B, then taking a pit stop along the way at some other point is not going to shorten our travel at all, right? You can't add in a pit stop and find a shorter distance. And if you're curious about that last property, that's what's called the triangle inequality. So you can look that up on like Wikipedia or something if you're interested in that. But really, those are the only properties that we require a metric to have. As kind of a weird example that doesn't really model the real world, one of the first examples of a metric that you might learn about is something called the discrete metric. So the way that we define the discrete metric is if we're trying to find the distance from point A to itself, then that distance is going to be 0, right? We always want the distance from something to itself to be 0. If we're trying to find the distance between point A and point B, then the distance is just going to be 1. It's just always 1. And you can check for yourself if you want that that distance function actually satisfies all of the properties that I mentioned. But it's not really something that models our real world at all. If we tried to apply that to the real world, it would say that the distance from, say, LA to San Diego is the same as the distance from LA to New York. They're both just 1 unit apart. And that really doesn't model our world at all. Yet, it's still technically a metric. If you're curious about other weird examples of metrics, there's one that is sometimes known as the Chicago Suburb Railway metric. So to all my friends back in Illinois, you might have a better time of understanding what this is. Basically, the idea is that if you want to try to get from one suburb to another using only the train, you have to go through Union Station first. So you can feel free to look that up if you want. I think it's kind of a fun one. But there's like so many different kinds of metrics and on different spaces too, right? You don't have to find the distance just between 2 points. You can find the distance between 2 numbers, between pairs of numbers, between functions, and between other abstract objects. But really, mathematicians aren't always concerned with like specific examples of abstract objects or metric spaces as much as they are concerned with what's true about all of them. So that's where something like a proof really comes in handy and where you really have to go back to just the basic definition of what these abstract objects are. You can't really use any specific properties about them. But I don't really want to get too much into proofs right now, though I do have a lot to say about that. For right now, I really just wanted to leave you with kind of an idea of what math is more like. These sorts of abstract ideas and abstract objects that we deal with all the time. Metric spaces are actually one of the simplest abstract objects that we deal with, at least in my opinion. But they're definitely still confusing the first time that you come across them, especially when you see all of these weird examples. But like I said, math is a lot like a foreign language. So now you know, say, the new vocab word for metric space or metric. And maybe the next step in your learning is going and looking at more examples of metric spaces so that you know how to identify them when you actually see them. And that's kind of what happens when you're learning a foreign language anyways. You got those exercises where it's like, match the picture with the vocab word. And that's kind of what happens in a math textbook all the time, is they define something and then they're like, here's all these examples. Mathematicians do this all the time where we're constantly learning new words because we see them somewhere and we're like, I don't know what that is. So you look up a definition and you try to find examples to help you build sorts of intuition about the object itself and maybe some of its properties that it has. And then you go and do more reading once you know a bit more about it, and you try to see if you can apply it to, say, your own research or if there's other interesting questions about those objects themselves. So math is really kind of this tedious process where you're like very confused for a while because you just don't know what's going on, but then you practice and practice and practice some more. You build more intuition for the objects that you deal with until finally you maybe answer a question or you find more and more difficult questions and all of a sudden you're confused again and the process kind of restarts. It's very difficult at times and it's often very stressful, especially as a student when you have things like homework and tests that you have to do as well. But really, like, the way that some of these abstract ideas just seem to align perfectly is so beautiful, and I wish I could explain it to everybody. But again, I would have to teach you kind of a full new language first just to be able to tell you about like I think the fundamental theorem of Galois theory is incredible. It's absolutely amazing, but I can't really explain it to you unless you know all the definitions that go into discussing Galois theory, which there's a lot. Anyways, I hope this is at least a somewhat informative explanation as to what my life has been like as a math student. And until next time, bye.